Alright, let's move on to radioactive decay. So, radioactivity was discovered by a gentleman named Antoine Becquerel. You can read all about his little story here. But many of us know more about radioactivity, or we kind of associate it with the Curie, so Pierre Curie and Marie Curie. So they did extensive work on radioactive materials, and in the process they discovered some new elements like radium and polonium, and they've realized that those are actually both significantly more radioactive than uranium. So Marie Curie lived quite a bit longer than she lived longer than her husband. He died in an accident. So Marie Curie discovered that intensity of radiation from uranium compounds wasn't affected by other materials in the compounds, and that really it was only dependent on how much uranium was present. So she concluded that radioactivity was a process that resulted from within the nucleus itself. So Marie Curie is what for her extensive work in essentially physics and chemistry. She got the Nobel Prize in physics in 1903 and in chemistry in 1911. So to date, she's the only person to have a Nobel Prize in two different scientific categories. And if I recall, I believe this might not even be true anymore. I think I have to look back. I think Linus Pauling might actually also have that honor, but she was the first. So Marie Curie's dedication to science did come at a price, though. Her work with radioactivity eventually led to her death. But even though she did die doing what she loved, her contributions to science cannot be understated. Like, they are so profound. So like, we owe her a great deal of debt. Unfortunately, she did pay with her life, but her contributions were not in vain. So Rutherford and others, they determined we have three forms of nuclear radiation. We have alpha particles, which is just a cute way of saying a helium-4 nucleus. We have beta particles, which is going to be a high-energy electron, if we're talking about beta negative. And then we have our gamma particles, so this is just going to be a high-energy photon. So we could generally, initially what we did to classify radiation is we classified the penetration ability of radiation. So alpha particles, they don't have great penetration power. They can travel about 5 centimeters in air before they get stopped, and they can't penetrate skin. So if you want to protect yourself from alpha particles, a sheet of paper or a few centimeters between yourself and the alpha source is more than enough. So we'd say that its hazard's low. It does, however, have a high ionization potential. The reason for that is an alpha particle is a huge, compared to a beta particle, and a gamma particle not having mass, alpha particle is quite massive. So if you get an alpha particle inside the body, let's say you have some like elements in your body, and we have these valence electrons here. An alpha particle is quite massive. So it can come in and it can easily knock electrons out of orbits, and it can ionize things inside your body. It can cause ionization inside your body. Because it's so massive, it's almost like a wrecking ball in there. So it can come in, knock out those valence electrons, and cause ionization. And your body is very finely tuned in terms of its biochemistry, so ionizing it is not really that good. So the hazard's low because it's hard for the alpha source to get in you, but if it does have high ionizing potential. Beta particles, they're moderate in terms of their ionizing potential just because they're not as massive as an alpha particle, and their hazard's still quite low. So they'll travel about 30 to 50 centimeters in air, and they can penetrate into the body by about a centimeter. If you want to stop an alpha particle or a beta particle, a thick piece of cardboard would be sufficient. And then the gamma particle, it will travel the greatest distance, and it can penetrate right through the body. So since it generally passes through the body, it has low ionizing potential, but it does have the greatest hazard because it can start to alter structure of DNA and stuff. So for protection, we usually want to talk about thick layers of metal. So usually like several meters of concrete or several inches of lead. So you'll notice ionization hazard, they're kind of opposite to one another. So if you have high ionization, you're a low hazard, but if you have low ionization, you're a high hazard. And of course we can see that if we place our different radioactive sources in a magnetic field, they are going to curve based on our hand rules. So our alpha particle being a positively charged particle, we would use our left hand. We have the magnetic field coming out of the page in this case. So if we were to do that, and we have our dots going into the page. So our alpha particle, is going to use our right hand. So if we do that and we have our fingers coming to the page and we kind of track our velocity along this path, we will know our palm is going to point towards this direction, so that's telling us our alpha particle is going to curve this way. The beta particle, being oppositely charged, is going to curve in the opposite direction. It's going to have a smaller radius of curvature because it has a smaller mass. And then our gamma particle, being neutral, will not be affected by the magnetic fields. When we deal with radioactive decays, we are going to deal with conservation laws. So we're going to deal with conservation of charge. So it basically states that the electric charge of the system will not change in a decay process. So whatever it was before the decay happened, the total there is going to be equal to the total after the decay process happened. So if we're using conservation of charge, we're using physics principle number 7. We also have a new conservation law, the conservation of nucleons. So the total number of nucleons present before a reaction happens has to equal the total number of nucleons after the reactions happen. So this is going to be physics principle number 8. So what we're going to be doing in a reaction, when we're dealing with conservation of charge, in our nuclear reaction, we're going to have like everything written in the form AZX. What conservation of charge tells us is that the total Z value on the left side of the decay equation has to equal the total Z value on the right side. And then for conservation of nucleons, the total A value on the left side has to equal the total A value on the right side. That's what we mean by our conservation of charge and conservation of nucleons. So let's look at these decays. Are they possible? So we have polonium-214 decays into lead-208 plus an alpha particle. Is this possible? Let's check our conservation laws. So let's check conservation of nucleons. So before the decay, I have 214 nucleons. After the decay, I have 208 plus 4. Well, 214 is not equal to 208 plus 4. They are not equal, so this decay cannot happen. We don't even have to check the Z values, because once one of them fails, the whole thing is not possible. But we're going to check Z. Let's check conservation of charge. So I have 84 on the left side here. Is this equal to 88 plus 2? No, it's not. So conservation of charge also fails. So this reaction is not possible. Let's check. Does thorium-230, is it possible for it to decay into radium-226 plus an alpha particle? Let's see. So we're going to check our A values. 230. Is this equal to 226 plus 4? Yes, it is. So this respects conservation of nucleons. But it's an all or nothing. It has to respect both laws for it to be valid. So it has to respect charge as well. So we have 90 on the left. Is this equal to 88 plus 2? Well, yes, it is. So this decay respects conservation of charge and conservation of nucleons. So this decay is absolutely possible. Now, what we'd like to look at is we'd like to actually start looking at the different types of decay. So atoms are kind of like people. They crave stability. What we're going to find is heavy nuclei, because they have all those protons and neutrons in the nucleus, they're going to be really unstable. And what they're going to do to reach stability is they're going to eject nucleons. And they're going to eject it in the form of an alpha particle, or helium-4 nucleus. So the general form that we're going to have for an alpha decay is we're going to have our parent element on the left side, and then it's going to decay into this daughter element plus this alpha particle. So this is what we start with. Then when we get rid of the alpha particle, we're going to have a new element. Now, do you have to remember this exact formula for the decay? No, as long as you can remember that in an alpha decay, one of the main products is an alpha particle, you can use your conservation laws to work backwards and figure out what the daughter element is. So let's do that in an example here. So we want to find the alpha decay process for uranium-238, and we're going to name the daughter element. So we always have to tell you by which means these elements decay. You're not expected to know that. So uranium-238, so we know the atomic number is 238. We have uranium. So we go to the periodic table, we're going to find that the atomic number of uranium, so if I go to this really, really outdated periodic table, this is from like the diploma from many, many years ago, uranium is going to have an atomic number of 92. So with that, we want to decay by an alpha decay. So first off, as long as we know that an alpha particle is one of the products, we can sort of work backwards on our conservation laws. Because then we have to ask ourselves, okay, 4 plus what is going to give me 238? So we're going to have 234 for our atomic mass number for our daughter element, and then 2 plus what is going to give me 92. So that is going to be an atomic number of 90. So if we go to the periodic table, the atomic number of 90 is going to be represent thorium. So uranium-238 will decay into an alpha particle, and thorium-234. So the daughter, this is the daughter, this is thorium-234. So our very heaviest of elements will tend to go through alpha decay. So beta decay is a little bit more complicated. We actually have two types of beta decay. We have beta negative decay and we have beta positive decay. So beta negative decay is going to happen when a nucleus emits a neutron, and then that neutron itself is going to transform into a proton, an electron, and a very, very small particle known as the antineutrino. We'll talk more about that in a minute. Now, very formally, what's going to happen in a beta negative decay? We are going to have our parent element. It's going to decay into our daughter plus this neutron, and then this neutron is going to decay into a proton, which is going to become part of our daughter element, plus this beta negative particle or electron and this antineutrino. This is very complicated. This is meant to be more of like a formal way of writing it. For us, that's messy. This is what we want to remember. So we have our parent element decays into our daughter element. They have the same A values. The daughter element increases its Z value by 1. We have that beta negative particle, the electron, and then we have the antineutrino. So think of this thing, and the way to remember whether it's a neutrino or antineutrino, so we have beta negative. It's almost like we have a negative sign above the antineutrino. So that's the way to remember. Or, anti also has the word N for neutrino. Anti negative, not neutrino. So anti has an N, negative starts with an N. However you want to remember that, that's fine. So to work out the daughter element, the big thing is if you can remember the beta negative particle and the neutrino, or the antineutrino, then you can use your conservation laws to work out the daughter element. For conservation laws, the neutrino doesn't have a charge, nor is it a nucleon. So your A and Z values for a neutrino are both 0. We don't actually write those, but that's just for you to be aware. It will not contribute to your conservation laws. So let's write the decay equation for iodine-131 if it undergoes beta negative decay. So iodine-131, we have the atomic mass number. If we look on the periodic table, iodine is going to be element 53. Now, it goes by beta negative decay, so we need two things. First of all, we need our beta negative particle, and we also need our antineutrino. Now, the antineutrino will not contribute to our conservation laws, so we have to ask ourselves, 130 is going to equal 0 plus 0 plus, 131 is going to equal to 0 plus 0 plus, but we need 131. That helps us with our conservation of nucleons. For charge, -1 plus 0 plus what is going to give us 53? Well, the what here is going to be 54. So this is how we kind of use these to help us deduce, kind of work backwards, what the daughter element's going to be. So element 54 is going to tell us the actual element in question. So we have xenon. So the daughter element that we get in this reaction is going to be xenon-131. Now beta positive decay, very similar or similar-ish. So what we're going to have is we're going to have a proton. It's going to transform into a neutron, a positron, and a neutrino. So what's going to happen for the decay is it's going to look like this. So we have our parent element. It's going to decay into a daughter element with a reduction in the Z value by 1. This time we have our beta positive particle, so its charge is going to be +1 instead of -1. And then we just have the regular neutrino here, so we don't have the antineutrino. The positron is what we call the antiparticle of the electron, which we'll talk about more later. It has all the same properties as the electron. The only difference is the charge. It has a charge of +E as opposed to that of -E. So we want to write the decay equation for zirconium-95 if it undergoes beta positive decay. Again, identify the daughter nucleus. So zirconium-95. So we have 95, we need to find zirconium on the periodic table. So zirconium is going to be element 40. Now this is going to decay into, we have the beta positive particle, or the positron, plus our neutrino. So the symbol for the neutrino kind of looks like a hooked V. It's the Greek letter nu. And now let's look at our conservation laws to deduce the daughter element. So I have to ask myself, 0 plus what gives me 95? Well, in beta positive or negative decay, A value is not changing. So we're going to have a 95 for our atomic mass number. Then I have to ask myself, 1 plus 0 plus what gives me 40? So the what here is going to be 39. So we have that reduction in the atomic number by 1. So element 39 on our periodic table, this is going to be yttrium. So the daughter in this case is going to be yttrium 95. Now, we've mentioned this neutrino a little bit, and the neutrino came up about is because when they looked in the late, like in the 30s, when they were looking at conservation of energy in nuclear decays, what they had found is that the laws of conservation of energy and conservation of momentum didn't quite hold up. Like, okay, we've accounted for our daughter element and the beta positive, beta negative particle, but there was a teeny tiny piece missing. It didn't quite all add up. So it kind of looked like mass disappeared. A gentleman named Wolfgang Pauli, he proposed that this missing piece of mass and energy was actually carried away by this small particle not yet discovered, what we now refer to as the neutrino. So the neutrino was discovered on paper well before it was actually experimentally verified. And the thing is, the neutrino being quite small and having an extremely, extremely tiny mass, like we're talking 10 to the minus 37 kilograms, it took a while for it to be discovered. It was eventually discovered experimentally, so experiment did eventually catch up with theory on that one. But yeah, that one took a little bit of a while to get, just because again, that teeny tiny that teeny tiny mass, and of course no charge, so it's not going to interact with fields. Now we've talked about our three of our four fundamental forces. The last one has to deal with the weak nuclear force. So when in beta negative decay, when we had that neutron transforming into a proton, electron, and antineutrino, this is actually due to this thing called the weak nuclear force, and it interacts with anything that has quarks, which we'll talk about later what a quark is, and it only reacts with leptons that are responsible for beta decay. We'll talk about what a lepton is later. Basically, it only reacts with anything that has quarks, and then electrons, neutrinos, and their respective antiparticles, so the positron and the antineutrino. So what we're trying to say here is that the main reason that beta negative and beta positive decay happens is because of this weak nuclear force. The last type of decay that we can look at is gamma decay. So gamma decay is just all about getting rid of energy. So usually you'll have an atom in an excited state. To get it back to a lower state or a lower energy state, we're just going to have it emit a photon in the form of gamma radiation. So generally you'll have something that looks like this. This AZX decays into AZX plus gamma. This little star here, this is just meant to denote that our element is in a slightly excited state. So you're probably not going to see a lot with writing out gamma decays. What's probably going to happen is you're going to be told the energy of the gamma particle and be asked to calculate something like its frequency or its wavelength. So like we have a dyspropium 152 atom, it's going to undergo gamma decay by releasing a photon that has an energy of 2.928 mega electron volts to go to a lower energy state. So we'd like to write the decay equation for dyspropium 152, and we'd like to determine the wavelength of the emitted photon. So dyspropium 152, so dyspropium, we are going to write that it is element 66. So dyspropium, it's in an excited state, so we'll put a star next to it, and then that's going to decay into a lesser excited dyspropium 152 plus this gamma photon. Now, the gamma photon does not contribute to the conservation laws because it's not a nucleon, so it's going to have an A value of 0, and the gamma photon doesn't have a charge, so it's going to have a Z value of 0. So to calculate its wavelength, we know that E is equal to hc over lambda, so that tells us that lambda is going to be hc over E. Well, this thing is in mega electron volts. I might as well use Planck's constant in electron volts seconds. Just makes that a lot easier. Electron volts seconds, 3 times 10 to the 8 meters per second. And then I want this in electron volts. So mega is going to be 10 to the 6. So instead of mega electron volts, we're going to have times 10 to the 6 electron volts. Now for sig digs, Planck's constant and speed of light, they are constant, so they don't count for sig digs. So only this energy counts for sig digs. So I have 4 significant digits there. What that's telling me is I need to have 4 significant digits in my answer. So what we're going to get here is we're going to get about 4.242 times 10 to the minus 13 meters. So that is going to be the wavelength of our photon that is emitted from this gamma decay. And its wavelength is in the appropriate range for gamma decay, so we're going to be pretty happy with that. Now, we've talked about kind of heavier elements releasing, alpha particles to achieve stability. So when we talk about stability, we find that for elements to be stable, we want to have a neutron to proton ratio of about 1 to 1. When we get to heavier elements, we want it to be about a 3 to 2 ratio. So the belt of stability, or the band of stability, this is a really common diagram in nuclear physics. It just shows like where our stable elements happen to be, or our stable atoms. So this line represents that ratio of neutrons to protons being 1. And then this shows us kind of like our stable elements as we move up. We kind of get to this point C. This is at the atomic number 83. Once we hit atomic number 83 or more, so when something has 83 or more protons, there will be no more stable matter. So the belt of stability ends here. Once we exceed this point, no matter is going to be stable. It's always going to want to decay. Depending where we are on this chart is going to kind of give us an idea of what type of decay mechanism we're going to undergo. So for example, if we're in region A back here, we have too many neutrons. So if for too many neutrons, we'd like to achieve that stability. So to achieve that stability, we have to undergo beta negative decay. In region B, we have way too many protons. So to deal with that, what we want to do is we want to have beta positive decay to reach stability. And then region C, we just have way too many nucleons. So in order to get to our stability, we are likely going to undergo alpha decay. This is not something that you actually have to know for physics 30. This is more of an advanced thing. It's just something to point out. And you may also see something like this called the radioactive decay series. How something decays, it can go by different methods. So for example, we're starting out here with the decay of uranium-238. So you'll notice for the first little bit, it's kind of got a linear path. Like, okay, we got an alpha decay, beta, beta, alpha, 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 alpha. But then when we get in these regions here, we have choice. Maybe it goes here, then here, then here, then here, or maybe it goes here, 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 here. We don't know, or sorry, once we get to here, we have more possibilities. On a proper diagram, you'd have percentages listed over these decay telling you what's the probability it'll go by that decay route. So this graph here is what refers to as a radioactive decay series. What it's meant to show you is that there's multiple paths to get the stability, and which path is taken is going to depend entirely on the laws of probability. Again, you don't actually have to know this for Physics 30, just something to point out. So the last thing, as you are probably very well aware, nuclear radiation and radioactivity in general has hazards. So the two major risks associated with radiation is radiation sickness and genetic damage. Now, you're always being bombarded by radiation. At this moment, you are being bombarded by cosmic rays. They're going to cause little slight bits of damage to you. Your body can repair that, no problem. If you get bombarded with large amounts of radiation, then your body's going to have a slightly more difficult time repairing that damage. So the big thing is when you're working with radioactive materials, you want to be safe, and there are some certain considerations we want to take into effect. You want to certainly decrease your time around radioactive materials or stay away from it if at all possible. You would certainly like to, if you can put some distance between yourself and the radioactive material, also great. But if you absolutely have to be near it, use protection. Shielding is your best friend in this context.